What's up?
Should make the click noise.
Oh, I have the audio off. It all depends on when the last time I had the sound on. Oh, and apparently we did not have a video from last class. I don't know what happened. I uploaded something, and then I deleted all the videos after it was done uploading, and then I got the warning saying this was a duplicate video that you uploaded. So I must have clicked the wrong whatever. So that one's gone because I've already deleted it. Yeah. It just happened to fall into the. I usually delete my videos about once every week and a half when it gets over like 20 gigs. And I just decided, okay, I'm going to delete these. And
can't you like restore your laptop to like a previous date and get that back?
yeah, I don't care enough for that because it's you who's missing this video. And it was just us going over the homework. But before I forget, we will not have class this Thursday. I will be putting up, I don't know if it's going to be an assignment, a quiz. At the very least, I'll put up something. It won't be due on Thursday, but some activity for you to do Tuesday in place of class. But we're also going to have a midterm. I will probably put up a study guide for the midterm for this class as well as those of you who are in the 250 class from earlier today. I'll probably put up a study guide for both of those. Then we'll review on Tuesday. And the actual exam will be a week from Thursday, which is right before break, right? That's legit? That sound right? Okay. Like we have class that day?
Well, let's see.
Wait, next Thursday.
Yeah.
So
Break
you
is
can
the
have.
following week.
Okay, so I'm
Yeah,
good?
But yeah, that's fine.
So we'll have
Yeah.
class on Tuesday the following week.
No, I want to do the midterm next week so we have grades in plenty of time. I'm just making sure I'm not picking a date for the exam that's like during a break. So we do have class a week from a week. Okay, that's when the exam is. So I'll put a study guide up between now and Thursday, probably Thursday morning or something like that, or Thursday night if I forget to do it. But it'll be up, and then you can look at that over the weekend or whatever and formulate questions, and then we'll talk about the exam on Tuesday and actually have the exam on Thursday. Make sense? Okay, I just didn't want to forget to tell you that we will not have class on Thursday this week. Okay, so let's talk about binary addition. We're kind of leading up to the midterm. I want to finish up this slide set or get pretty close to it. Most of it's dealing with math with stuff. So kind of like when we've done conversion stuff, when we did the conversion of binary to decimal, octal to decimal, hexadecimal to decimal, and vice versa, we kind of notice there's a pattern. It's always the same thing. Now, we've been doing addition for years, correct? You know, we kind of lost practice. We don't do the write down the stuff and do the decimal addition where you carry stuff, but we remember it. It's something we've done before. Now we just pull out the calculator and do it. Well, something we're going to see here is that there's a pattern to that as well. So we're going to start off by looking at binary addition, and we're going to kind of talk about a couple of ways this works, and then move into hexadecimal addition. So when you're looking at binary addition, when we, let's kind of look at it this way. Here's the two numbers, 0011 and 0101. Everything above here is carry bits, I think. No, those are the carry bits. So we're actually adding three numbers together. So binary accounting for carry adds, 4 new scenarios, blah, blah, blah. So 1 plus 0 is a 1 with no carry. 1 plus 0 plus 1 is a 0 with a 1 carry. 1 plus 1 plus 0 is a 0 with a 1 carry. 1 plus 1 plus 1 is a 1 with a 1 carry. Now my question is, what is this 1 carry? What does this mean? We've been doing carries for a long time. You know, we have these carry bits. But what does that actually mean? So if I have the number, let's just throw a slide up here. And let's just do this in decimal. So I have the number 38. And I'm adding that to 56. All right, so that's the math I'm going to do. 8 plus 6 is what? 14. So what do I write?
Carry the 1. Then
Carry the 1.
4 on the bottom.
So there's my 4. And we carried a 1. What does that 1 mean?
Because that is the value that you can have in, well, it's kind of, it's 1 more than the value that you can have in one single placeholder.
See, we're almost tricked in decimal. In decimal, we say, oh, we had 14, so that's 4 carried the 1. And how do we get our 14? We just have a 1 and a 4. That's 14. This 1 is actually a 10. This is the tens place. So this is 10 plus 4. So this is 4 in the ones place, 1 in the tens place for a 14. Does that make sense? So when we carried, we actually carried over a power of 10. This is a 10. Make sense? When we add here, 5 plus 3 is 8 plus 1 is 9. Or do we add 10 to it? We add 1 to it, right? That's 9. Well, what happened to my 10? It's there. It's 1 in the tens place. So this is a 9. That makes sense? So when we carry, we are carrying a base over. All right? So since this is base 10 arithmetic, when we carry a 1, we're carrying a 10 over to the next power of 10's place. Does that make sense? So we're going to see the same pattern here. If we have a 1 plus a 1 plus a 1, that gets us a 3. 3 is not a legal binary number. So what are we going to do? We're going to carry a power of 2, leaving us 1 left. So that's why we have a 1 carry 1. 1 being 1 power of 2. That makes sense? Exact same thing we just did in decimal. It just seems weirder because we're doing it in binary. All right? So that's binary addition at the high level. So what I want to do here is I want to write a formula. And we're going to do it for binary first. We're going to write a program that takes in 2 numbers and adds them together at the binary level. Not convert it to decimal, add them, convert it back to binary. Not that one. All right? And after we do that, we're going to start looking at how subtraction might work and deal with complements. All right, so we'll start off in Eclipse. So this is 325. All right, let's just get all this crap out of here. I don't know what it was for, but we don't need it. All right, so we want to write a function that's going to return a string. So the answer is going to be in string format. We can return a binary number. And it's going to call add bins. It's going to take in 2 strings, a binary, the first binary number and the second binary number, B1, B2. And we want to do that math. Okay? And just like the slide was talking about, we have 4 patterns. And I always think it's dangerous to think about things like this. You know, it's almost like memorize these 4 situations. A 1 plus a 0, well, in this particular case, when we're adding 3 bits together, we have 4 patterns. If we're adding 2 bits together, we have less patterns, right? But the point is, memorizing patterns, I think, is problematic. I always kind of relate this back to how many of you like math? Let's go that route. I know a lot of people don't like math, right? That's why you come to computer science at Concordia. Totally a true statement. That was Dr. Locklear and I when I first got here. I came from a pretty strong engineering background, teaching at schools that have very high math requirements, and also going to a school that had very high math requirements. So coming here and watching, he just kept dumbing down the math requirement because you're trying to keep student population up, right? I mean, it's an interesting thing at Concordia. It's more of a liberal arts school, but also being a science department in a religious school becomes problematic because you need to keep your classes up, and they didn't know they had me, the secret weapon. It's popular to shut up. Well, in any case, him and I would argue about that. That I wanted you guys to take like every math class we offered, and then have them like invent additional math classes. Like when I was in college, I took a class called Combinatorics. Yeah. I had a crazy teacher. His name was Samson Adeliki. Guy was awesome. He was a black dude, but with a British accent. And he brought this bucket of like colored chalk to class with him. Because the white chalk that came like with the classroom, that was when we had chalkboards. Are there even chalkboards on campus?
Somewhere.
Oh.
Like storage room.
Okay, like a storage
In a
room.
dark corner.
Right. But yeah, he'd bring his own colored chalk to class. He'd draw stick figures.
There's one chalk in the prayer room. Beneath the chapel. Oh, yeah.
But when he taught stuff, he would draw like a stick figure. He's like, "This is Mary. Mary was a very diligent student, very diligent." And that was my British accent thingy. But yeah, that's how he sounded. Trust me. I don't know if that's British accent or whatever. That's how he sounded. But in any case, the reason I asked the question is, you know how you take those math classes and the first pass, you have all these theorems and postulates and stuff like that you just commit to memory, right? Or back in the early days of graphing calculators, what I did on my homework, this was in high school, when we had a test, I would literally, there was a drawing type program, I would draw all the formulas into my calculator. I'd spend like 5 hours putting the formulas into my calculator to the point that when I got to the test, I didn't need it. Well, yeah, that didn't exist back when. Yeah.
Big database.
Yeah, my graphing calculator was made of oak. We had a choice of 2 different finishes. So, in any case, what's up?
It's probably similar to his graphing calculator thing.
So that catches the sun just right in power.
No, it's gonna wind up.
The mouse he has inside of it runs on sun, water, and cheese. Home churned. All right. Well, so anyways, the point I was getting at here is one, I guess, kind of trick that I learned in math, maybe through experience. When I got into grad school, I actually had to use a bunch of that math that you just kind of memorize formulas and get through when you're in the classes. You kind of know what I mean? Like you got a big calc test, what do? You memorize all the formulas so you can get the right answers on the test. You don't know why those are the formulas. You just know that they're the formulas because that's what the teacher said, and now you memorize them. You learn all the tricks for doing derivatives or integrals or something like that. Everyone's like, oh, which trick is this? So it becomes a memorization problem rather than a I understand what's going on problem. So I kind of don't like, then when I got into grad school, I had to go and figure out what all that crap meant. So I had to go relearn all that math stuff. I forgot it since, but at some point I understood what it all meant. But I think there's far more value in understanding how something works and why it works than just knowing that this is the answer. So I don't like this idea of memorizing patterns. That's kind of why I'm harping on this. When you're carrying it, you're carrying in this case, a 2's place, so it's a power of 2. Blah, blah, blah. So I don't like this crap. Ignore that. Just know the answer because of why it's the answer. All right, so we're going to write a formula, or a method, I guess, called add-mins. This guy's going to take 2 strings as parameters, and we're going to add these guys together. Now, we probably could have left we had a pad method in here, I think, to make sure these guys were the same length. We're going to have to rewrite that again quickly. But we want to start both of our strings off at the same length. So we might be looking at something like, I still have my, I took it out. So for instance, we might have 1 0 1 1 as our first string. And let's just say we're adding to that 1 0. Okay, so if that's what we were actually adding, we want to pad this first one with 2 zeros at the beginning, just for the sake of working with even length strings. So if we're doing this math, one plus 0 is 1 with no carry, correct? 1 plus 1 is 2, so that's a 0 with a 1 carry. So we have a carry up here. 1 plus 0 is 1. 1 plus 0 is 1. So 1 0 1 1 plus 0 0 1 0 is 1 1 0 1. That make sense? All right, so we want to write a method that does that math. Okay? And then we're going to write, ultimately we're going to rewrite that to work for any base. Math in any base. So we're going to start off, B1 and B2 may be different lengths. So let's see. We need to make sure that they're the same length. So let's have something called numbits is equal to, we want the length, the maximum length between B1 and B2. So we have something called math.max, B1.length, B2.length. So nice little helper function that exists in Java for doing just that. If we didn't have that, what would we have done? If B1.length is greater than B2.length, then numbits is equal to B1.length. Else, numbits is equal to B2.length. Could have written it ourselves, but this is a nice, quick way of doing it. So now we're going to have a quick little method, static string pad bits string s and a integer numbits. And we'll say, let's actually call it zeros to add is going to be equal to numbits minus s dot length. So if we wanted to have a number of bits being 5 and s's length was 3, 5 minus 3 is going to be 2. That's how many zeros we need to pad onto it. Make sense? Write a little loop for its I is equal to 0, I is less than zeros to add, I plus plus, and we'll just say s is equal to 0 concatenated with s. And we are safe doing this. This is an interesting little trivia fact dealing with strings. This will make a lot of sense to those of you who are in 250 here in a couple of weeks. But strings are passed by value, not address. So even though they're objects, we get a copy of this string. So when we modify s in here, we're not modifying a global version of it. So it's okay for us to modify this version of s. When we start talking about arrays, we'll see that arrays work the opposite way. If you start modifying the contents of an array inside of a method, you're actually modifying the global version of it. You're changing it in memory. All right, then in the end, we'll just return s. So this will add the appropriate number of zeros onto the front of the string. All right. Then we're going to say B1, this is back down on our add bins. We'll say B1 is equal to test dot pad bits B1 and numbits. B2 is equal to test dot pad bits B2 and num bits. So now we know B1 and B2 have the same length. They have the appropriate number of zeros in front of them. We maybe just did a bunch of work and didn't change them at all. Potentially. They may have both already had a length of 3, in which case we didn't have to add any bits to it, but we still went through the process of trying to add bits. Go ahead.
If this added zeros to both.
It wouldn't.
Okay.
Because one of them is going to give us our maximum length.
Yep,
Yeah, what he was concerned about is what if we padded both of them? And because of where we got our num bits from, it couldn't. Num bits was based on the longer of our 2 strings. So one of those strings we're not touching, the other one we're adding some zeros to. Potentially, we're not adding zeros to either of them. All right, so now B1 and B2 are the same length. So now we know we're dealing with a situation that looks like this. All right, so now we're going to walk from the end towards the beginning doing the math. All right, so each time through, we want to look at the current digit. So we're going to start at the end of those strings. Now we know the strings are currently the same length, so it doesn't matter if we do it based off of B1 or B2's length. So we're going to have a string for our answer. We'll start that off as the empty string. Now we'll have a for loop. I starts off at b1.length minus 1. I keeps going as long as it's greater than or equal to 0, and we'll subtract 1 from it each time. Okay, so this will take I on a journey from the end of our strings towards the beginning of our strings. So this is going to go look at these digits, then look at these digits, then look at these digits, then look at these digits. Okay? Now, each time through, we're going to look at B1's digit and B2's digit for addition. And we need to get the numbers out of there and add them together. Right? How do I turn a 1 into the char 1 into the number 1 and the char 0 into the number 0? Integer parsing will do it, right? So let's give ourselves an int temp just for right now. And we're going to set temp equal to integer.parseInt b1.charat I. Now this guy is currently a char, correct? How do I turn a char into a string? Because integer.parseInt requires a string. How do I turn a char primitive type into its string equivalent? So I have the char 0. How do I make it the string 0? Concatenate the empty string. So we'll say that right there. Make sense? Okay, so I'll throw this comment out again. I said it earlier, but most of you who've had me for multiple years have heard me say this many times. All hard programs are made up of a bunch of easy parts. You have to solve the little baby step you're solving in front of you before you can solve the bigger problem. Okay, so we just solved a little tiny problem, that is, I have a char, I need a string. Okay? So this is going to give us an integer, the integer version of the string version of the char at bucket I from B1. And I'm going to add to that the integer version of the string version from b2.charat I. Okay? So all we just did there is we either added a 0 plus a 0, or a 0 plus a 1, or a 1 plus a 0, or a 1 plus a 1. Those are the 4 things that may have just happened. And temp holds the sum. So the sum will either be a 0, a 1, or a 2. Make sense? All right. Now, if it is a 2, what do we want to do? That's when we carry. correct? How do we handle carries here?
We use mod.
Okay, tell me what you're trying to accomplish.
I mean, you mod it so that you can, keep track of or calculate the amount over you're going, and then you have the number that you can store and manipulate from.
Okay, I think I see where you're going with it. You're trying to deal with the powers. So it go from the ones place to twos place to fours place, and if you use the mod, you get that number that's left over. I guess what I'm saying is if we have a 2 here, which is the biggest number we can have, we know we have a 1 for our carry, correct? So that's a power of 2 for our carry. So we have 1 power of 2 to move over to the next column. Where do we store those carry bits? Because in the math we just did here, we added this bit to this bit. We didn't consider, is there a carry bit? We would never have a carry bit the very first time through. But after that, it's all fair game, right? So what if, so if I have this 1 plus 0, in fact, actually, let's just create the scenario for us. Forget about the answer for a second. 1 plus 1 is a 2. Since it's a 2, I know I need to record something here. And I know I need to carry something else. That make sense? So I'm going to have to store those carry bits somewhere. So maybe I have a third string that starts off as the same length as the other ones. Make sense? And maybe we go in and we modify that string with our carry bits. So it started off, we did a 1 plus a 1 plus a 0, which gave us a 2. And 2 says we should do what? 2 says our answer is, here, we'll just put all zeros in here for right now. 2 says our answer is a 0. Carry the 1. That make sense? Now, how did I get a 0 here and the 1 here? So I had a 2. This is the number I really, really, really wanted to write down there. Not legal in binary. Okay? Can't write it. It's not a 0 or a 1. Base 2, legal digits are 0 to n minus 1. So I know that we just know the pattern, and we can say, okay, that's a 0, carry the 1. How do we mathematically figure that out? So maybe we get over to this mod idea. So how do you want to mod this?
We'll mod it if there's a remainder of 1 we have to the empty string.
Okay. Well, so what are we modding? So I have a 2. I'm going to mod 2 by what? Okay, why 1?
Because you want to have a remainder so that it can carry over into something else. And, I mean, if 1 goes into 2 times, then
What is 2 mod 2? Okay, so 2 goes into 2 one time with a remainder of what? 0. So that could be our 1 here and our 0 here. Let's go back to a slightly different example where we wouldn't have a carry. 1 plus 0 is what? 1. How many times does 2 go into 1? 0 with what we're left over? 1. Make sense? So we're going to do the math between all 3 of these. So 0 plus 1 plus 0 gives us a 1. We record the remainder where? As our carry bit? Or as this guy here? 1 mod 2 How many times does 2 go into 1?
0.
It goes in 0 times. So this is the quotient, right? That might have been my testosterone phone call. That's an awkward, weird phrase to put in the middle of the...
Video's gonna get banned on YouTube now. Inappropriate things.
I don't think that's inappropriate.
No, I don't.
Yeah,
You know how people get on
it's just creepy.
Yeah.
Yeah, it's not inappropriate, it's creepy.
Creepy.
It's 2 different things.
Just mark out Halloween in the middle and people understand.
I'm pretty sure there are plenty of other things that people
You think?
complain about.
I always think it's funny when my wife and I are watching Big Bang Theory, and her and I are very much like Sheldon and Amy. So there's all sorts of conversations the 2 of them have that my wife and I have. And my wife is like, she keeps throwing it in my face during the show. And the funny thing is it's very much like Sheldon. I don't get it. There's all sorts of stuff in that show that I miss because I don't realize that Sheldon's acting funny. Other than everybody else's reactions, it seems normal to me. Interesting fact, Sheldon has Asperger's as well. I would say he's weirder than I am, but he might not be medicated.
Give it a week and we'll know.
No, take more than a week. I think you have to take 6 months to, it's called titrate. They have to titrate you off the drug. 2 weeks per, I think 25 milligrams or something. So I think is that 6 months? Coming off 300 milligrams?
Just screws everything.
I don't think they get down to the individual day. I think the idea is come off a bit slowly. All right, so we're going to record the quotient up here and the remainder down here. That make sense? Okay. Now, couple of things we can do here to make this work. Just for simplicity's sake, I'm going to go ahead and we're going to actually make an array to store our remainders. Not our remainders, to store our carry bits, rather. So I'm going to create an integer array called the CBs, the carry bits. And this guy will be a new integer array of size num bits. All right, so that guy will have the same number of bits in it as we have digits in B1 and B2 after these 2 lines. So these guys are strings, these guys are arrays. Make sense? Kind of could have turned everything into arrays, but we didn't. Just deal. Now I'm just going to quickly loop through and fill up the CBs with zeros. So just go through every element in that array, and we'll say the CBs at bucket I is equal to a 0. Initially, all of our carry bits are zeros. And the reason we made it an array as opposed to a string is if we look back here, if this was a string and we needed to set a carry bit here to a 1, we would have had to rebuild the whole string. Now I can just go in and say, this guy is a 1. Make sense?
What happens if you get a carry on
On the far end? Yep, we're going to have to deal with that. It's called an overflow bit. If we're doing this like how a computer does it, and we'll talk about, I think somewhere in here is the IEEE standard. Yeah, there's the IEEE thing. So it talks about how the machines actually do the math. So we're trying to mimic that. You didn't hear that yet. All right, so there's a possibility we might have something called an overflow bit over here, which is a final carry. And what would we do with an overflow bit? Drop it down, right? All right, so we'll handle that in that special case if we get to that endpoint. All right, so when we get here, we know that B1, B2 are both the same length with potentially some zeros in front. We know that the CBs is an array that has the same number of buckets in it as B1 and B2, currently all filled with zeros. Now, when we have our answer, temp, that is B1 at the current character plus B2 at the current character, we now need to store some stuff. And what are we going to do? Well, in our, the CBs, so the CBs at bucket I minus 1,
Lowercase s.
thank you. CBs at bucket I minus 1, which again, we might run into a problem with that, but right now let's just assume that's legit because we're setting, if we're currently doing math here, we're setting this guy, I minus 1. Okay? We'll say the CBs at bucket I minus 1 is equal to temp divided by 2. The integer division, the quotient. Make sense? And then we're going to say that our answer is going to be the modulus, the remainder. So we'll say answer is equal to whatever answer is currently equal to, concatenated with, except this would build it backwards. All right, so we need to put our answer onto the front. So we're going to say answer is equal to the empty string, even though we don't need the empty string, I'm just putting it in there, I like it. So the answer is equal to the empty string concatenated with temp mod 2, and I'll throw that in parentheses. So whatever that math is, that's the remainder, concatenated with whatever answer currently is. That make sense? Okay. So the first time through, we'll do a 0 plus a 1. Well, actually, we didn't do the 0 plus the 1 plus a 0. We need to actually do that. Right now, for temp, we're just doing B1 and B2. We also need to add in the CBs. Well, I want to see what happens there, because I'm definitely not... Oh, I am. I had it was out of the order. I pressed enter. Just trust me. I'm right. It kept capitalizing the S.
Oh.
And I say it. It's because I was capitalizing the S. But it was a constant pattern. So I'm going to take CBs at bucket I, which the very first time through, that'll be a 0. Right? Because we filled it up with zeros. We only start changing it after the first time through. So we'll take CBs at bucket I. We're going to add to that the integer version of the current character in B1. And we're going to add to that the integer version of the current character of B2. So now we have the CBs at bucket I minus 1 is equal to, so the next carry bit is equal to temp divided by 2, integer division. And answer is going to be the remainder onto answer. Okay? Now, we mentioned that we have a problem with carries. I'm saying I minus 1 here, and we know that when we get to this point right here, so here in this example it's 1 plus 0 is 1, carry the 0, 1 plus 1 is 0, carry the 1, 1 plus 0 is 1, carry the 0, 0 plus 1 plus 0 is 1, but then it's going to try to carry the 0 because we're always setting the CBs at bucket I minus 1 equal to something. That make sense? Okay. How can we resolve that? This extra bit over here is called an overflow bit. So we need to put that somewhere. So what we're going to do is we're going to have an int called overflow. And that guy's going to start off at 0. We're only going to set the CBs at bucket I minus 1 equal to it if I is currently not 0. If I is not equal to 0, then do that. Otherwise, overflow is equal to temp divided by 2. Now, in our mind, from a programmer's perspective, we might consider this as the problem of, okay, well, why didn't I just make the CB's array 1 bucket bigger? And then operate in it with an I plus 1. That when we finally got down to I, I'd be at bucket 0. We could have done that. But think about this in terms of the hardware inside of a computer, because that's what we're actually learning about what happens inside of a computer. We're just doing it through software, okay? Because it's a good way of showing that stuff. But here's an example of where flexibility in software doesn't necessarily mimic flexibility in hardware. Software is easy. It's like, oh, you need another variable? Create it. The most we'd ever have in any math problem, whether we're dealing with an 8-bit problem, a 32-bit problem, a 64-bit problem, whatever, is 1 overflow bit, correct? We only need to handle 1 bit. And is that something that we can consistently use? Can we use one of their hardware registers for an overflow? Remember those hardware variables built into the CPU? We could use one of those guys as an overflow bit, right? So we're using these general purpose registers just to hold a simple bit. Typically, there actually is a register. I want to say it's called OP, because I think it holds operators and overflows, but there might be 2 separate ones. I might be dating myself from last time I actually looked at CPU architecture. But in any case, we're going to have a single piece of hardware memory used to hold these overflow bits. We don't have this flexibility of saying, oh, let's just have 32 bits here, but we're going to have a 33-bit something else. Does that make sense? That piece of hardware doesn't exist. We'd have to have this custom piece of hardware just to deal with our carry bits, where we can do it with an overflow bit pretty easily. Go ahead.
What if you were adding a 1 and a 1? Then the overflow, there would be 2 bits because you'd have to add a...
But with an overflow bit, you'd never have 2 bits. You'd have 1 overflow. The overflow is what flowed off the end here when we're out of crap.
What if you had a 3
carried over from the previous one?
Okay, so you want this situation. You want a 1. These guys were already 1 and 1, right? These guys were already 1 and 1. Just forget the math over here. This is the situation we ended up in.
Yeah.
Okay, so that's 1 plus 1 plus 1 is 3. What's 3? 3 divided by 2. How many times does 2 go into 3? 1. So we have a carry of a 1.
Okay, plus 1.
And then a 1 here. Does that make sense? Still only had 1 overflow bit. Okay, so that's how we can handle that generically. I know this math doesn't work out to this 3 ones. Just deal with it. All right, so we're going to write our little program here in a similar fashion. So we either used our overflow, little guy here, or we used this. Now let me ask you a question here. Did we even need to keep track of this array? Or could we have done everything with an overflow bit? As we walked through this, could this have been the overflow bit? Then this is the overflow bit, then this is the overflow bit, then this is the overflow bit. Did we even need to waste extra memory up here to deal with it? Or did we just need to remember what the overflow bit was? Does that make sense? So, I can get rid of this array. There's no reason for us to store all the carry bits. We just have to know what the last carry bit was so that we can do the math with it. So we're going to keep our overflow, but we're going to get rid of this array. Now we no longer have to fill that array. Now notice the overflow started off as a 0. No carry, correct? Now, temp will be overflow plus the integer version of our two chars. And now we can always set overflow equal to temp divided by 2. That make sense? Now, when we're done with this for loop, we may not have our final answer. Can we always tack overflow onto the front of the answer? Is that okay? If overflow is a 1, if in the end we had this situation where we have this extra 1, then our final answer should be this, correct? Pretend like the math over here is correct. We just dropped that overflow over. Dropped it down, right? What if it was a 0? Is that still correct? Does that change the value of that number at all? No, it didn't change it at all. Now, some things to consider here though. From a software perspective, we can certainly drop this down and just, the easy formula for it would be to just say, oh, whatever the overflow bit is, let's just tack it on. So we just say this. We'd say answer is equal to the empty string concatenated with overflow concatenated with answer. We'll just tack on the final overflow bit. Whether it's a 0 or 1 doesn't matter. It'll be correct. Right? So we can do that. And that'll work from a software perspective. But for a hardware perspective, if we're actually implementing this on let's just say the CPU, and we're adding these two numbers. So this is one binary number. Let's just say that these are nibbles. Just use this as a nibble. So we have a nibble, and the result. The result's going to have a fixed size. Depends where we're putting it. So some of the things we run into when we're writing, and we're going to do this after midterms, we're going to start looking at low-level languages. And one of the things we have to consider is, let's say, sorry, you got this, okay. So let's say that I have the number 5. Let's see, well, let's say it. Let me just write it in binary, even though actually when you do a low-level language, you actually use decimal and it does the conversion for you, but let me just write it in binary. I might say I want to move 1111 into AX. I might have those backwards actually. Doesn't matter for this little example. We'll call this pseudocode, just in case it's wrong. All right. So AX is going to be the name of one of our registers. All right. Now, let's just say that this guy is an 8-bit register. Okay. What's actually going to get moved in there is that. It'll fill up the entire 8 bits. So it'll zero it out first, then add it in, using its interesting math algorithm to put it in there. Okay, that gets down to how is stuff stored in a variable, in a hardware variable, not related to what we're talking about right now. Okay, but let's say that this was half of a register, a nibble, and we tried to put 1, 1, 1, 1 in there. No problem. But let's say we were trying to store that into a nibble. Will that fit in a nibble? It won't. These are some of the problems that we run into when we're dealing with low-level software, low-level programming languages. We can't just, and we deal with it at the high level, but it's so much more flexible. We know that we can't put a number greater than positive 2 billion into an int in Java. But rarely do we have to, right? We don't run into that situation very often. If we do, our backup plan is along. If that's not good enough, we can go over to some of the object methods in the objects in Java. We can look at big integer, which allows us to have an arbitrary size integer. Doesn't matter how big. It's implemented in terms of linked lists. So, we don't have that issue. With your computer, with the hardware side of things, you have a finite number of hardware resources that you have to do all of your mathy stuff with. We don't have this luxury of, in the middle of solving a problem, just inventing a new piece of cache. Kind of make sense? It really makes the problem interesting. You have to solve, when we talked about CPUs, we say CPUs they're a resource on a computer and they have a collection of magic tricks, things that the CPU knows how to do. All right? All problems we solve on an Intel-based computer, we have to solve in terms of that CPU's magic tricks. Not just what it knows how to do, but what it's capable of storing. There's going to be a limit to the total amount of data that CPU is capable of storing at any point in time. And we have to solve the problem we're currently trying to solve in terms of that. Well, with our programs, we still have that limitation, but we only have to solve problems within the 8 gigabytes of RAM that we have. That makes sense? Whose problem is it to take our Java program or our C++ program or our C# program and turn it into the low-level equivalent that better work on this architecture of our CPU? Whose problem is that? It's the compiler. I don't remember. How many of you took the compilers class last semester? I was in this group. So we teach a compilers class. Since it was offered last spring, it won't be offered it won't be next spring, but the spring after that is when it's offered. I think it's every other year. So I teach our compilers class, and that class is about taking a high-level language, and we've all learned about it in here, in the 250 class that you've had. You know that the job of a compiler is to convert a high-level language into a low-level language. And that sounds so easy and pretty on paper. What we just did, what a compiler does, is we're saying it's going to take your loosey-goosey Java language, where you don't care about memory. Not enough space, let's just make a bigger variable. No problem. It's going to take all that carelessness and convert it into something that will run on the system resources that is your Intel CPU. That's a hard problem to solve. And compilers just keep getting better and better and better. In the early days of compilers, the only goal was for them to be accurate. Like, make sure this stuff right here, this low-level language, is functionally equivalent to what you said up here. Not efficient. Just functionally equivalent. Our modern-day compilers, they've gotten so good that they make bad programmers look like good programmers at low level. So you could write some really crappy code at the high level, and the compiler makes you look like a saint. They're really, really advanced. But it's a very different problem that you're having to solve at the hardware level. You have a limited number of resources to work with. When we're programming, we don't think like that, do we? It's like, more variables. No problem. But
Is the compiler the person's job to, let's say someone had a 8-bit L1 register cache and the other one has 16. Is it the compiler's job to switch? You know what I mean?
No, because the compiler switching to a low-level language has a one-to-one relationship with the CPU. So every line of low-level language translates into one, I usually call magic tricks. One magic trick the CPU knows how to deal with, and it's the CPU that knows how to deal with the caches. So the low-level language would deal with putting things in and out of registers, which are known architecture portions of a CPU. But if you're writing a program, that program needs to work the same whether you're dealing with the Intel Core i7 or the Intel Core i7, whatever the current steroid version of it is with the crazy L2, L3 cache. You know, you shouldn't have to have a program recompile to work on that guy. So those caches are things that the CPU internally can use as buffer space to solve some of its problems. So it's the CPU that manages that extra space for different problems rather than the compiler rating it for more cache space. So the compiler is always working directly with hardware registers. Does that answer it? Okay. But I mean, it's a good question, and it kind of keeps us going down this path that I'm talking about here where things are so complex at the hardware level. It's really amazing how far we've come today with that disconnect between software and hardware. You know, it's really, and this kind of relates to our operating systems class, where we have this piece of software that lives between our hardware and us, the end user. So we're writing high-level code, which gets translated into low-level code. In Java, it gets translated into Java bytecode, which then gets interpreted into low-level code, which then gets run on the CPU, which then actually spits stuff out, uses your system resources and things like that. Really interesting problem. Okay, so in any case, we're going to have this one overflow bit that we can deal with. And that's easier to rely on that guy always being there than rely on the CPU to provide us this 33-bit or 9-bit or 65-bit chunk of memory to store all of our carry bits. When we're thinking about this like a hardware engineer, we don't need to know about all those carry bits. We just need the current carry bit when we need it. Make sense? So typically, we would not, from a hardware perspective, we would not automatically concatenate the overflow bit onto our answer. We can do that in our program here, because what would happen is, if the program you were working with, if the next step after it did this addition, if it was interested in that carry bit, it would specifically ask for it. It might say, what's the value of this hardware register, which might be everything that was in answer minus the overflow, then is there an overflow? And that overflow might mean something. That makes sense? And if it needed to put those two values together, it could choose to do that. Here's our entire answer. Okay, what's in this register plus the overflow bit. That's the full answer. But it keeps it separated in general. All right, we'll go ahead and return answer here. So this should take two binary numbers, add them together, giving us the binary result. So we'll do a system.out.println test.add_bins. And let's go ahead and 1011. Well, here, let's actually do real math here so we have the correct answer. All right, so that's a 1, a 0, a 1, a 0, and a 1. That would be the carry. So that's a 1, that's a 0, carry 1, that's a 1, that's a 0, carry a 1, and there's the 1. So this should give us 10101, where we do have a 1 in the carry bit. So 1011, 1010. One zero one zero one. 10101. That makes sense? Now, interesting point here. So I'm actually skipping ahead a couple of several slides. What if I wanted this to work for hexadecimal?
You would need to let it know the base that it's in. Correct.
I'm telling you it's the base, but yeah, you would maybe take another thing called the down here, the radix or something. But let's say I wanted to write the same function for add hex. Add hexes. What would change? So instead of the 2 here, we'd have a 16. Instead of the 2 here, we'd have the 16. What else would change? Binary is easy. Only has zeros and ones. What are the legal digits in hex?
Through F.
Through F. So 0 through 9, A through F. That make sense? So if I want this guy to work for add hex, let me actually just do add bins, and I'll duplicate this method just so we can have the two sitting next to each other. We're definitely going to be dividing by 16 here. We're definitely going to be modding by 16 here. But we need to account for that conversion between letters and numbers. When we do our addition, we need to treat A's as 10s and B's as 11s and C's as 12s. When we record our answer, we need to treat 10s as A's, 11s as B's, 12s as C's. Does that make sense? Questions about what I just said? But the pattern is going to remain the same. And what you're going to see is when we solve the add hex thing, and we come up with the correct solution, which may or may not deal with char at and index of. Hint, hint. The hint hints are probably going to be important since I'm about to give you a homework assignment. Okay? Once you get that working, you'll see that you can apply that exact same algorithm to adding any bases. Does that make sense? Literally any bases. Okay, now, a couple of points of interest though. When we're dealing with hex, what are our possible carries? Think about base 10. If you're adding any two base 10 numbers, what is the largest your carry can ever be? One. Binary, what's your largest your carry can ever be? What do you think the largest your carry could be in hex? 1. Why is that? Why are carry bits always either 0 or 1? Besides the fact that it has the word bit in it. Where a bit is a 0 or 1, right? Why is it that that carry bit is always a 0 or a 1?
Because the value before it can't, the values before it can't add up to equal more than the next bucket.
Okay, well, but we know that that carry bit scales. So like for decimal, the carry bit's worth a 1 in the first column. It's worth a 10 in the next. It's worth 100 in the next. It's worth 1,000 in the next, right? Because it keeps going up by those powers of 10 in that case. For binary, it goes up by powers of 2. We're representing a 1. But that 1, depending on where it is, might be 10 to the third power, or 10 to the fourth power, or 2 to the third power, or 2 to the fourth power. That makes sense? In hex, it could be 16 to the third power, 16 to the fourth power. How many of those? The most you can have is 1, but the other part of that equation is which position is that carry bit currently interacting with? And that's what scales it. This is a 16, but we're in the third power place, so this is actually 16 to the third power if this guy was a number in and of itself. That makes sense? So carry bits never have to hold something bigger than a 0 or a 1. We'll never have to hold anything other than a 0 and a 1. It's always a 0 or a 1. Whether we're doing base 3 math or base 4000 math. Base 4000 becomes very difficult. Conceptually it works, but we don't have enough letters. We'd have to invent our own alphabet. But it would work just fine. That'll actually be an interesting thing in the future. When our values get so large that we no longer have an alphabet to, like right now with hex, we just use A through F, right? We can go all the way up to base 36 by using the rest of the alphabet. What happens when we need more than that?
Chinese.
Add the Latin numbers.
Yeah, I mean, it's going to be interesting. At some point, somebody's probably going to have to invent the counting system standard.
Or you just start using lowercase ones after you run out of
Suppose you could have it be right now they're used interchangeably. I think the standard says they should all be uppercase, but I see them used interchangeably all the time. So at this point, I don't think you can use upper and lowercase. Somebody at some point, I mean, we don't know how this could be very far in the future. We got lots of bases we have to go through before this becomes a real problem, right? But
Break into the Chinese alphabet.
so interesting problem. All right, so for Tuesday, I'll give you extra time to work on this assignment. So for Tuesday, I'll put this code up as a starting point. Write add hex such that it works for adding 2 hexadecimal numbers together. So that'll be your assignment between now and Tuesday. Between now and Thursday, I will put up a study guide for the, I say study guide, I'm basically going to tell you the things that you need to understand for the midterm. Then on Tuesday when I'm back, we will talk about the midterm. You can ask questions. Now, I'm only going to miss Thursday this week for those of you who have any other classes. I'll be here Friday. I'll be here tomorrow. Just Thursday I won't be here. Okay? You will see me the rest of the week, just not that one day. So I'll go ahead and put this up on Angel, and I'll see everybody next Tuesday.